In this class, we are working one example in finite difference, and the objective of today's class is to set up the equations to solve a problem. So before we start, I'm going to review some of the boundary conditions that we already developed for the class, or the equation that we already developed. So the first equation that we developed was an equation for a node that is in the middle. So for a node that is in the middle, so what we did was a balance of energy, and the balance of energy is minus QA, QB, QC, QD. So all the heat transfer in the different sections A, B, C, and D, plus the heat generated if we have heat generation, and that should be equal to 0. So that sets up the equation for a cell, and this particular cell that is in the middle. So we went over all the heat transfer and flow rates, and we obtained this equation. This equation that is minus 4 times the temperature in the middle plus the temperature in the north, temperature in the south, temperature in the east, temperature in the west, plus this term, which is Q dot multiplied by the volume of the cell that we are analyzing, delta X, delta Y, and divided by K, and that's equal to 0. So the next equation that we developed was adiabatic boundary condition. We apply the same concept, conservation of energy in all the different areas, A, B, C, D. The difference in these cells that is in the boundary is, first of all, the area, and therefore the volume is half of the standard one. And second is that Q at B is equal to 0. This element is equal to 0. So for QA, we have the temperature in the outside minus the temperature in the inside, multiplied by K, divided by delta X, because we are moving in perpendicular to the area A, and the differential of area is in the Y. And then QB is 0, QB is 0, and then we have QC, which is for this area. We have these two nodes, and we start with K multiplied by the temperature in the outside minus temperature in the inside, divided by delta Y, and multiplied by the area, and the area in this case is half of the area, so it's delta Y divided by 2. And then we do the same thing for D. So for D is temperature out. Temperature out is Tmn plus 1. I swapped the order, so I had the signs negative before, but this is the correct sign. So T on the outside minus T in the inside, multiplied by K divided by delta Y. And the area is dx divided by 2, because it's half of the area, plus Q dot, the heat generated in this volume, which is Q dot multiplied by delta X, delta Y, and delta C. But remember that everything is multiplied by delta C, so we can divide by delta C, so we don't put it. So we just put the area of this. So it's delta X, delta Y divided by 2. That's equal to 0. So if we reorganize, we realize that we have minus 2 times Tmn, the temperature in the center. So we are, first of all, we are doing is divided by K, the whole equation. So we divide by K, So this case cancel, this case cancel, this case cancel, and then we have a k in the last fraction, last term. And so when we count the temperature, so we have this Tmn, but it's multiplied by 2, and the same thing here, this Tmn, but is divided by 2. So these two are 2 times Tmn divided by 2, so that's Tmn, plus this one is 2 with a negative sign, and the rest of the term is Tmn minus 1, and then we have Tmn minus 1 divided by 2, and Tmn plus 1 divided by 2, and the last term, which is divided by k. And that's the equation for this case, for the adiabatic case. Okay, now when we have convection boundary condition, so what do we have as the heat at B? So what is QB? So that was to be a square cup question for you to work at home, but I'm going to develop here. So for the flow in this section QB, we have that the heat transfer at B is well, if we are going to follow the same procedure, it will be convection. So all of these terms have convection. So the difference in between all of these possible terms is how the temperatures is organized. So this is convection over here. So let me draw. So we have a fluid. A fluid is at temperature T infinity. So the area, it will be this area. So that will be delta Y and delta C if we consider the delta C. So all of them, they have delta Y, delta C as an area. So all of them are possibles. And we have then H multiplied by the difference in the temperature, which involves T infinity. And remember that the standard that we have here, the pattern that we have is that we have the temperature out minus temperature in. So temperature out will be T infinity and temperature in will be temperature at this node. So out T infinity, in Tmn. So that's case A. So Q is equal to H multiplied by T infinity minus Tmn multiplied by delta Y, delta C. So if we summarize for this element which has convection on one side, what will be the equation? Well, if we compare with this case, the equation in this case have QB equal to 0, and apart from that, all the flux should be the same for this case. So I'm going to copy this equation and add the heat flux at B. So the heat flux at B, so let me do it like this. So I'm going to copy this and I'm going to add the term for QB. One thing I forgot, this is negative because with the convection that should be the negative. So I'm going to add this term there. And so we are adding two additional terms, this multiplied by this. Oh, and we can get rid of the delta c, right? Because we are dividing everything by delta c. And so the two terms that we have are this and this, multiplied both by delta y. So that means that we have an additional tmn. So that additional tmn is plus h multiplied by, so that will be negative h tmn delta y plus h multiplied by t infinity delta y. So that are the two terms. So in conclusion, for this equation, there is something here. No, that's it. Yeah, so we can compact the equation in the following way. So we have minus 2tmn minus h tmn delta y plus all these terms tm minus 1n plus tm n minus 1 divided by 2 plus tm n plus 1 divided by 2 plus this term with t infinity, so ht infinity delta y plus q dot delta x delta y divided by 2 equal to 0. So further simplification that we can do here is we can put this together. So we have minus 2 plus h delta y multiplied by tmn plus the rest, and the rest is the same. So we can keep the rest the same. Additionally, we could multiply by 2 if we want. So if we multiply by 2, we'll have 2, these 2 cancel, these 2 cancel, 2, and these 2 cancel. That's optional, but this is the equation that we can have for a cell with convection in the right hand side. And so the equation can change depending if the convection is on the bottom, the convection is on the top part, but the pattern will be exactly the same. Now let's go to the problem that we want to solve for this class. So the problem that we want to solve, and that will be part of the homework. So what you will do in the homework is to verify all the questions that we develop here and put them in Python and solve for the temperatures. And a second part will be how to plot those temperatures in 2D. So let's start by considering, by looking into the problem. So in this example, what we have is we have domain. So this is our domain. On the top part is insulation. We have some insulation. So this is an insulation on the top and insulation on the bottom. So we divide this in 4 cells. So 1, 2, 3, and 4 cells. So we have nodes from 1 to 9. So this is the numbering that I decide, like global numbering for the nodes. On the left hand side, we have a conditions that we have a temperature constant of 50 degrees. So for this node, so we know the temperature, which is 50 degrees Celsius. So at 7 and 8 and 9, the temperature is known. So we already know that from a start. So that T7 equal to T8 equal to T9 equal to 50 degrees. Apart from that, all the temperatures of these nodes are unknown and we want to solve it. The second boundary condition is T infinity. So we have a fluid on the right hand side, and that fluid is at a temperature of 10 degrees. So this is 10 degrees Celsius, and we have a convection coefficient of 20 watts meter square Kelvin. So all these nodes are subject to that boundary condition. For this problem, we take delta x equal to delta y equal to 0.01 meters, and what we want to find is the temperature at nodes 1, 2, 3, 4, 5, and 6. To do that, we have to set up the equations for each one of the cells. So this cell, this cell, this cell, and therefore this, and this. So we are going to start in order. So we are going to set up the equation for node 1. So for node 1, which is convection, and in this particular case, the cell that we have to take is this one. So the cell is, this is our cell. So balance of energy. So this is a quarter of the area. See, this is just 1/4. So, but the idea is the same thing. And we have one section which is insulated. So let me put the names of the area. So on the left hand side we have A, on the right hand side we have B, on the bottom that will be C, and the top will be D. So we have that Q, because this is insulated, we have that Q at C is equal to 0. So we don't have to consider that. So for our first area, which is the area A, what we have is, we start to set up our equation. So we have K multiplied by the temperature out minus the temperature in. Temperature out, which is 4, minus temperature in, which is 1, divided by delta x, because we are moving in x, and multiplied by the area, and the area is delta y, and this should be divided by 2 because it's half, so divided by 2. So this is, let me put it here, this is minus QA, and so we continue with B. B is convection boundary condition, so convection is H multiplied by the temperature out, which is the temperature of the fluid, so it's this, I'm going to write it like T infinity minus the temperature in this case will be the temperature at 1 minus T1 multiplied by delta Y. Remember that this is the one that we developed in the last part, in the last section, and the area is delta Y divided by 2. And so this is Q at B with negative sign. At C is 0, so we don't have it. Yes, at C is 0, and at D, so let me put 0 minus Q at C, and at D is the top surface, so we have K multiplied by the temperature out, which is T2, out is T2, in is T1 for this section, T2 minus T1 divided by delta Y, because we are moving in delta Y, and multiplied by the area, but again this area is just half the area, so that's plus times delta X divided by 2, and plus the heat generation of this section, which is Q dot multiplied by the total volume, but this is like 1/4 of the cell, so that will be delta X, delta Y, and delta C, but we are already canceling delta C, remember, and this is divided by 4, and that equal to 0. So this term is Q at B, and this is the heat generation, so energy generated, and that should be equal to 0. So this is the equation for node 1. We could leave this equation like that, and Python will take care of solving for each of the term, for simplifying the expression, or we can simplify it. So if we simplify it, the first thing that we could do is multiply by 2. So if we multiply by 2, we are going to cancel this. So well, let me do this. So we can multiply by 2 and divide by K. And okay, and we can simplify delta X and delta Y in this case and in this case. Nothing else. So the first the first part is T4 minus T1, and we multiply by 2, so that 2 is cancelled, and divide by K, plus H T infinity, the 2 is cancelled, the delta Y is not cancelled, minus H T1, the 2 is cancelled, delta Y, plus 0, so that's 0, plus, and the next term is T2, T2, and the last one is Q dot multiplied by delta X, delta Y, and we are multiplied by 2, so the 4 becomes, wow, that was a very long line. Sorry about that. The 2 becomes, and the 4 becomes 2. and that should be equal to 0. So further on we can reorganize the T1s. So let me put it here. So we have this T1 and this T1. So we have minus 1 plus h delta y multiplied by T1 minus this T2 is positive plus T2 plus T4. So we already have the T1s, the T4, and we have two of this term which are constants. So plus h t infinity delta y plus q dot delta x delta y divided by 2 equal to 0. Okay, and so this is our first equation. As I mentioned before, we could just have left the equation like that and input that equation into Python, and Python to be able to simplify or solve the equation without simplifying. We'll see that in the next class. Now we continue with the second node that we have is node 3. So what happened with node 3? Node 3 is very similar to node 1, right? So if we consider this and this, they're very symmetric. So for node 3, what do we have? So we can actually reuse this equation in terms of this node. So how do we do that? So the first thing that we we have to follow the pattern for this. Okay, remember that this is insulated. So let me put the insulation here. Let me do it in a different color. Okay, so they're completely symmetric. So in this case, we have temperature 1 multiplied by this factor. So in this case will be temperature 3. So we have minus 1 plus delta h, plus h delta y multiplied not by T1 but T3, plus we have T2, which was the temperature at the north. In this case will be the temperature at the south, and it by chance is the same thing, T2. So plus T2 plus T4. In this case T4 was the temperature in the west, so and the temperature in the west in this case is T6, so plus T6 plus h multiplied by t infinity delta y, t infinity delta y, because it's corresponding to that area, and plus the heat generated plus q dot delta x delta y divided by 2 equal to 0. So that should be our equation for node 3. So in this case was much easier because we use the fact that is symmetric to this case. Now we can continue with node 2. Node 2 is an adiabatic, so it should be easier. So for node 2, let me do it in this. not 2, and the area that we are considering is this. Well, it's not adiabatic, it's convection. So we have T infinity and H for the fluid that is outside. And that's the same case that we have for the quiz example. So we can go and copy that equation, but let's do it for the sake of the exercise. So we're considering the areas are A, the opposite is B. Let's put C and D. Really, it doesn't really matter how you number them. The important thing is to do the equations in the proper way. So what do we have for A? For A, we have K multiplied by T out minus T in. T out minus T in. So it's T5 minus T2. Multiply and divided by delta X and multiplied by the area, which is delta Y. Plus B. V is convection. So convection is H multiplied by T out, which is T infinity, minus T in, which is T2, multiplied by the area, which is delta Y. Now C. We have K multiplied by the temperature out, which is out is 3, in is 2, so T3 minus T2 divided by, we are taking the differential in this, so it's delta Y divided by delta Y and multiplied by delta X. The area, and the area is delta X, but this is only half, so we divide by 2. Delta X, this is multiplied by delta X divided by 2. We should have delta C, but remember, delta C is cancelled all the way, so it's not that it's in reality the area. And okay, so we have, this is QA, this is QB, and this is with the negative. QC, this is QC. Now QD, so plus QD is very similar to C, so it's K multiplied by T out, so out is this, in is this, so it's 1 minus 2, so T1 minus T2 divided by so because we are moving in this way perpendicular to the area, so we divide by delta Y, and the area is this section, which is again half the area, so this is delta X divided by 2, plus the heat generated, so the heat generated is Q dot multiplied by the volume, delta X, delta Y, and delta C, but we are dividing by delta C. And this is half the area, so this is half of, well, delta X is half, if you want to do it. Delta Y and delta X is 2. Half delta X divided by 2. And this is equal to 0. So let me put this for the sake of, we are labeling everything. So that will be QD. And this is the heat generated. The last one is the heat generated. Now to simplify, we can multiply the whole equation by divided by K. We can divide by K, and we can multiply by 2, so to get rid of the denominators here. So when we do that, we can simplify. we have for T2. Okay, let's start with T1. So we have any T1. So we have T1 and this term divided by K. Okay, let's simplify the delta X and the delta Y's because we are assuming that they are constant. Okay, so we have T1 in this case, and it's multiplied by 2. So we have it's multiplied by 2, but it's divided by 2. So in general, we have T1. For T2, we have this T2, which is negative and is divided by 2. And we have this T2. Remember that the central node here is T2. This T2 is multiplied by 2. This T2 is multiplied by H and delta Y. And this T2 is just divided by 2. So we have 2 divided by 2, so which is make it 1, plus this is 2, plus this term here. So what we have is, and then we multiply by 2. So we have plus 2 T2 plus this term, and plus this term here, plus H multiplied by delta Y. So this is all the T2s that we have. You can verify all this algebra on your own. Now we have, and this is multiplied by 2, multiplied by these 2. Now we have T3, so we have T3 over 2, and it's multiplied by 2, so we have 1 T3. And what else do we have? T5. We have T5 again, that is multiplied by 2, plus 2 times T5. Yes, and plus what terms are left? So the terms that are left are this and this. So the first one is H multiplied by T infinity delta Y, and this is multiplied by 2 and divided by K. And the last one is Q dot delta X delta Y, and it's divided by 2 but multiplied by 2, so the 2 cancel, and this is equal to 0. So this is the equation for node 2. So we continue. So we already have node 1, node 2, and node 3. We have to go with node 4, 5, and 6. Okay, node 4. This is the element that we have. This is our cell. And so node 4, we have insulation on the bottom. And the good thing is that node 6 will be the same. So we only have to develop the equation for node 4, and node 6 will be, well, not the same, but it's symmetrical. So what do we have? So let me call the areas. So this is A, B, C, and D. So the general equation will be minus QA minus QB minus QC minus QD plus Q dot delta X delta Y, This is divided by 2 because it's the cell is half the cell, equal to 0. So we start with QA. QA is out minus in multiplied by K and multiplied by the area. So we have K multiplied by T out, which is T7 minus T4 divided by delta X, because we are moving in X and between 7 and 4, and multiplied by the area, which is half of delta Y divided by 2. QB, so we have plus K T out minus T in, out minus in, and divided by delta X and multiplied by the area. So out is T1 minus T4 divided by delta X and multiplied by the area, which is delta Y over 2. Okay, next we have C. C is 0, so C is 0. And next is D, and D is the top surface, so is K multiplied by T out, which is 5, minus in, which is 4, divided by delta Y, because it's degrading in this direction, and multiplied by the area, which is delta X plus Q dot delta X delta Y divided by 2 equal to 0. So again, we simplify delta X delta Y delta X delta Y delta X delta X and delta Y, and we divide by K. So we divide by K everything, so we have K here, and this K cancel, this K cancel, and this K cancel. And we can multiply the whole thing by 2. So we are multiplying by 2 and divided by K. Okay, so what do we have? Let's start with T1 to put them in some order. So for T1, we have T1 divided by 2 and multiplied by 2. So we have T1. And we don't have T2. We don't have T3. We have T4. So T4, we have this, which is divided by 2. T4 is the node in the middle, so we have several of those ones, T4, T4, and T4. So these two, the first two are divided by 2, and the last one is not. So these two half form 1, plus this is 2. So we have minus 2T4 multiplied by 2, 44. And next, 4, 5. We have 5, and this 5 is just 1, but it's multiplied by 2. So plus 2T5. And 7 is divided by 2 and multiplied by 2, so this is plus T7 plus the independent term, which is the last one, Q dot delta X delta Y, and this is divided by K, and the 2 is cancelled with these 2, so that should be equal to 0. Let me verify. We have 44, T7, T1, and 2T5. Yeah. And so this is the equation for not 4. Now not 6. We should be able to do something very similar because they are basically the same. So six is the same. So what we have in here, 4 was the middle, so it should be the same thing, minus 4 times t4. And now we have, in north we have 5, and then in south we have 5. So that should be the same thing, by 2 t5. And then we have east and west. And east and west, that we're considering just once. So in this case, east and west is T3 and T9. So I can put them anywhere, T3 and T9. And the heat generation is the same because it's the same volume. So Q dot delta X delta Y divided by K equal to 0. And that's it. So we have already the equation for 6. And the last one is the equation for 5. The equation for 5 should be the easiest one, right? Because we already, this was the first one that we did. Because it's a node that is in the middle. So for 5, so that will be node 5. The equation, and let's do it anyway. So this is A, B, C, and D. And we have for A, so again, this is QA minus QB minus QC minus QD plus Q dot delta X delta Y equal to 0. So QA, so is this, so is the gradient, which is out minus in divided delta X and multiplied by the area, which is delta Y. So it's K multiplied by T8 minus T5 divided by delta X multiplied by delta Y. And for B, we have plus K, T out is 2 and 5. 2 minus T5 divided by delta X and multiplied by delta Y. In C, we have K multiplied by T out, which is 4, minus T in, which is 5. So plus K multiplied by T4 minus T5 divided by delta Y, because it's in between the gradient in Y. So it's 4 minus 5 multiplied by the area, which is delta X, plus the last one is K multiplied by T out, which is T6 minus T5 divided by delta Y multiplied by delta X, plus Q dot delta X delta Y equal to 0. So then again, we can cancel all this delta X with delta Y, and we can divide by K. So when we divide by K, so all these are cancelled, and we divide by K in the last term. So we have, let's start with the one in the middle that is repeated in all the equations. So we have 1, 2, 3, and 4. So we have minus 4 times T5. Let me move it a little bit down. Then we have all the nodes around. So which are 2, 6, 4, and 8. Look, 2, 4, 6, and 8. So, and because the k is cancelled and all these terms are cancelled, we just add the temperatures. So it is plus T2 plus T4 plus T8 plus T6. The order doesn't really matter at this point. Plus Q dot multiplied by delta X delta Y divided by K, because we divide everything by K, and this is equal to 0. And that's it. That's the equation for node 5. And so what do we have to do next? We just have, as a result, how many equations? 5 equations. We have written 5 equations. And how many unknowns do we have? 1, 2, 3, 4. Sorry, we have 6 equations. So we have 1, 2, 3, 4, 5, 6. 6 equations and 6 nodes. 6 equations and 6 unknowns, unknown temperatures. So we have a system of 5 by 5 by 6 by 6, and that we need to solve it. And so the next thing is how to solve it in Python. Okay, thank you very much.